Alright, so we're now talking about magnetism 2. As we go through this, the lab part you're going to do in class, so we're not going to talk about that. So, we are talking all about forces. When a particle is in a magnetic field, it will not experience a force A. If it is not moving, we need movement. Or B, if it is moving parallel to the field. The particle is moving parallel to a magnetic field, it experiences zero force. When it's moving perpendicular, then we get a force. That's what we need. We are very interested. We need perpendicular movement. That's what we're all about. How do you find the direction of the magnetic force on a moving charge? So on a moving charge, it's QV cross B, and we're going to use our right hand to do it. So if we imagine our right hands here, fingers pointing this way, force goes with our thumb, velocity goes with our pointer finger, magnetic field goes with our middle finger, and we're going to make a gun with our hand, with our middle finger pointed in. You can do a better drawing of this than I will. I'm just going to describe it. So our pointer finger, we always want to move to point in the direction of velocity. Our middle finger, we always want to move to point in the direction of the magnetic field, and our thumb will consequently always point in the direction of force. Current carrying wire is very similar. The force on a current carrying wire is current times length cross magnetic field, and it's the same thing. Thumb goes with the force, pointer finger goes with the current, middle finger, ooh, it's a bad middle finger. Middle finger goes with the field, the other fingers don't do anything. Make a gun with your hand, stick that middle finger out, perpendicular to your pointer finger, and you have to line everything up. So, let's do some examples of that. Here we have two components to our velocity. We want to know the path that the particle will take. So, velocity in this direction, we have a velocity, and we'll call it V parallel to the field, and we have V perpendicular. This guy has no force. And the reason he has no force is because he is parallel to the field. So there's going to be no change to that velocity. No matter what happens with the other component, he's still going to be moving forward in some way because there's no force on that parallel part. Now if we look at the perpendicular part, we will experience a force. And it's going to be that QV cross B. So take your pointer finger, take your little gun, to point your pointer finger straight up, and you're going to have to rotate it so that your middle finger is going with the magnetic field and your thumb is going to give you that direction. Now, what's going to happen is that we are going to rotate. So initially we're going to go into the page, but we're going to come back up and we're going to make this helical pattern moving forward. Okay? This part moves in a circle. This part moves forward. Sorry about that. So, moves in a circle and moves forward at the same time. This is a helical pattern. Or a helical path. Alright? So, follow-up to that is, how does Earth's magnetic field protect us from harmful radiation? It traps it in that helical path around those magnetic field lines. And our evidence for that are the northern lights and the southern lights. It's those trapped magnetic particles interfering with the atmosphere. Describe how an electric motor converts electric energy to mechanical energy. Current in a field is pushed by the magnetic field. That current is the electrical energy. So when we have current flowing, we're using electrical energy. The interaction between that current carrying wire and the magnetic field causes it to be pushed. That pushing moves the object, and now we have mechanical energy. Here we're going to do the force. So our velocity is this way. Our magnetic field is into the page. So initially our force is going to be up. Now the particle is moving up, field's into the page, and if you do your little gun, that force is going to be directly over. Same thing with the current. You point your finger in the direction of the current, middle finger into the page, and your thumb points to the left again. It's not a really good left line. There we go. This next one, point your finger up. You have to rotate your hand a little bit. Point your middle finger to the right, and you'll see that the force is into the page. Force is into the page. So now we have current going into the page right here. The field is up. Sorry, current into the page, field is up, and that force is going to be to the right. And here we have a charge moving to the left. The field is down, and we see that we now have a force out of the page. That's how we draw out of the page. It's a dot. Current going to the right, field out of the page, and so the force is down. Current going up, field out of the page, so the force is to the right. Parallel, so we have force equals 0. Here we have our particle moving up, field out of the page, as a force to the right. And here we have the current coming out of the page, field to the left, so the force is down. And then again, the force is equal to 0 because these things are parallel or anti-parallel, but they're in the same direction. There's no perpendicular component at all. All right, now we have an experiment. This is difficult. So we want to state the direction of the magnetic field based on these two experiments. So you have to use your right hand, make your gun, point your thumb into the page for the first experiment and your finger in the direction of velocity. And you'll see that your middle finger can sweep out in this direction. So your magnetic field could be any of these things. It's a possibility. It's not guaranteed to be straight down. As long as part of my velocity is perpendicular to that magnetic field, I'll get that force. And we have experiment 2. So make your gun, point your pointer finger out of the page. Your thumb is going to be up at a 30-degree angle. And then you have a sweep of magnetic fields that could be into the page or out of the page, but it would be along this line because I know my force has to be perpendicular to my magnetic field. And since these two are describing the same magnetic field, what we can say is that my magnetic field, this is our horizontal line, my magnetic field is in the plane of the page and it's down at 60 degrees. That's our magnetic field. And we want to know which experiment describes a circular orbit, and then we want to know the other one. We only have a circular orbit when the velocity is perpendicular to the magnetic field. So, the experiment where the velocity is perpendicular to that magnetic field is experiment 2. The velocity is out of the page and the magnetic field's in the plane of the page. So they're perpendicular. In the other experiment, my magnetic field is this way, and if we go look up there, the velocity is in this direction. So what we're going to get is a helix that's parallel to the magnetic field. So, it's a circle when V is perpendicular to B, and when they're not, we get a helix that goes around that magnetic field, just like we talked about above.